basic rectangular shape in order to find the area. The next page that you have continues this conversation. Here we have an example of a column and a footing. Here we have an example denoting a type of material which would be shown in a schedule. Here we have a cross-section of a concrete slab, perhaps. It's got a lot of rebar in it. These little dots are pieces of rebar that's layering in this. Further on down the page, we have another type of concrete structure, and this is something that we are looking down at. And the dots represent the rebar. And sometimes rebar can be layered in something of a tic-tac-toe shape. In the modules dealing with vertical construction, you have exercises on how to estimate different pieces of rebar. And you might want to take a look at that now and see if you can easily estimate rebar, either if it's layered in a tic-tac-toe shape like this, or simply extending along a perimeter. By the way, this above little shape here might be written as number 5 rebar at 6 inches on center each way. The 6 inches shows us the spacing. The each way tells us that it's a tic-tac-toe shape. Now, although I show this as a tic-tac-toe shape, what's really going to happen is there will be a piece of rebar at the end here, and a piece of rebar at the end here, as well as up here and up here. And in trying to determine how long these pieces of rebar are, we have to keep in mind that when we place any type of steel in concrete, we do not want the steel to come all the way out to the edge of the concrete. And so we're going to have to cut back for the cover. The actual amount of cover will depend upon the use, but generally speaking, 3 inches is what is used. And so if we were given a dimension here that these bars were inside a footing that was of a particular dimension, we would have to cut back on all sides for that cover so that we would get the actual dimension of the rebar. The next exhibit shows a typical site plan for a residence. And what you have to do in your mind's eye when you first glance at something like this is kind of try to recognize the various geometric shapes and the kinds of things that questions could be asked about. And so this is the way the shape would appear to you in your mind's eye. And all I've done here is indicated that we have a trapezoid shape. Here we have rectangle, rectangle, triangle, trapezoid. Actually, there's a trapezoid, another trapezoid, trapezoid. We could create a rectangle over here. We might note that there is an indication for an angle in the corner over here, so we might have a property angle type question. And we might notice some key dimensions. The next exhibit that you have shows another point of view on a set of plans. Here, first of all, we have the fact that we are looking at a cut section. We've cut the building open. We're looking at now up and down dimensions. And also we want to notice that this is simply, this is simply an extension. These are extensions of one another. And this is called a match line. And the idea here is you might have to turn to one of the exhibits like this to find out vertical dimensions. And also to find out dimensions that take you from the center line of a column to the outside of the building. The next exhibit that you have shows another point of view. Now we're looking down at a roof framing plan. And in a moment we're going to look at a set of plans that you'll follow along with. But the thing to recognize here is that we are being shown different pieces of steel by their names. And we're also being shown different joists by virtue of a notation like this, which is resting on top of what really is an arrow. And these joists that are resting on this arrow are actually going this way. They're actually perpendicular to that arrow. So this is simply indicating that there are 12 of these joists perpendicular to this arrow, and everything the arrow crosses through and touches is one of those. The next exhibit that you have shows a column and footing schedule. We see elevations over here, and we see over here what is actually a portion of a column. And we'll go into this in more detail in a few moments when we look at the plans. Over here we're looking at locations that designate this particular type of column that's being described here. This next exhibit shows you an interior stairway in the building. And often they will ask you about a shape like this, and they'll be talking about the treads here that you would walk on. And the thing you have to keep in mind here is that treads have a relationship to the risers. And the relationship is that there's always one less tread than riser. The riser is the part that's going up, the tread is the part you're walking on. Now these types of stairways usually consist of little metal pans that are hooked in between two stringers and that often are poured full with concrete. And so you could be asked a question about the bolting of these pans. If every pan needed 2 bolts, how many bolts? Or you might be asked a question about the volume of concrete, in which case you'd have to measure how much concrete is in each pan and then multiply that by the number of pans. Or you could be asked a question about the surface area of the treads, such as placing some sort of non-slip material. Well, here you'd have to find out the area of each tread and multiply it by the number of treads. Whatever they ask you, however, has the common denominator in it of being able to accurately count the number of treads. This is difficult to do simply visually. So one suggestion that I have is if you zero in on the section that shows you what the dimension is from one portion of the stair to another, and then tells you how many risers are there, in this case 14 risers over 7 feet. If I have one less tread than riser, then from this point to this point, I must have 13 treads. Here I have another 7-foot distance, and so once again, if I have 13 or 14 risers, I have 13 treads. So to get from the first floor to the beginning of the second floor, I will have 2 sets of 13 treads. Also, in working with a detail like this, you have to be very clear on where the stairs actually end. In a 4-story building, the stairs could go only to the 4th story, or they could go through the 4th story onto the roof. And this would affect any type of calculation you would try to make. A final word of advice with questions like this, the general rule is you have to look at the dimension points and not the numbers. And you must account for something such as this little lip that's coming over the edge of this tread. This might actually increase by perhaps an inch the width of that tread. In your exhibits, you also have some particular details that are analyzed. For example, in this case, we're analyzing the cross-sectional area of a curb and gutter system. This is also explained in walkers. However, I take you through the steps here. What you're going to want to do is understand in general how to do this. And as you work with shapes, you'll see whether or not you're able to break a shape apart and analyze it this way. Now, what would the purpose be of finding the cross-sectional area of this curb and gutter? Well, the purpose would be if we wanted to know the volume of concrete necessary to pour this curb and gutter. If we knew the cross-sectional area and then multiplied it by the length of the gutter, we would have the volume. And that's what we use it for. The next exhibit shows you a cross-section of stairs that are leading into the building. We would be walking on top of these treads to get into the building. And in this type of situation, we might need to know the cross-sectional area of this because we, again, might want to know the volume. And so the way we would find the cross-sectional area of this shape is we would square it off and then subtract what's not there. And that will give us the cross-sectional area. Once we knew the cross-sectional area, we would be able to determine how long the entryway steps actually were. And then all we'd have to do would be to multiply the length of the steps times the cross-sectional area, and that would give us the volume. Another shape that sometimes is called to mind is a corrugated metal decking. And here we have such a decking, and it's filled with concrete. And we might want to find the volume of concrete for a given area. And what we have to keep in mind is the way to do that is we take the uniform thickness part. Here we have 3 inches of a uniform thickness. The bottom over here is an irregular thickness and goes to a peak of 1.5 inches. If we were to take half of the irregular length or thickness, in this case it's 1.5 inches. If we take half of that, which is 0.75 of an inch, and add it to the uniform thickness, 3, we would have an average uniform thickness of 3.75 inches. Now you got to keep it straight here because you're dealing with a very small amount of inches. You have not yet converted it to decimals, even though you're referring to it as 3.75. It's still 3.75 inches. To accurately convert it to decimals, you'd have to divide that by 12. But we could take this average uniform thickness and multiply it by the area that was being referred to, and that would give us the volume that we wanted. In your materials, you have two sets of exams. Each one is organized around a plan. And the first plan and exam that you have is dealing with a four-story Chamber of Commerce building. If you'll open up that set of plans, what we're going to do is go through these set of plans so that you can see the kinds of things you want to look for. And I'll show you how some of the problems relate to these plans. After we're done doing this one, you might want to take the second set of plans and look through it to see if you can identify the types of shapes and issues that we'll be going through with this set of plans. So if you'll take this set of plans out and open it to sheet number 1, we'll go through these plans. Although we would start by looking at sheet number 1, I like to look at the elevations first. So we're going to turn to the sheet that deals with the elevations. Here I'm going to take a quick glance to notice a couple of things. First of all, to get a general idea of what it is that's being described. I'm going to take a look very quickly at the elevations to see how tall the building is, and in particular if there's a difference in elevations between the first floor and then subsequent floors. I'll notice the fact that these are symmetrical buildings because they're only giving me an east and south elevation, and there's a note on this plan page that tells us that north and west are identical. And so I have a sense of how this building is going to look. Now I'm going to turn back to the sheet number 1, which is the site plan. The first thing I'm going to notice in this site plan is the footprint of the building itself, and I notice they give me the gross dimensions of the footprint. I might need to know this as a quick and simple way to determine if the building were in square, because knowing the proper footprint, I can calculate what the diagonal should be for the building to be in square. The next thing I'm going to do is notice if there are any angle points that are pointed out, and that indicates to me there might be an angle question, determining the angle here from the property lines. I'll look to see if there are sodded areas that have different names. In this case, there's sodded area number 2 over here. I'm going to notice the parking areas. I'm going to notice curbs that are running around this because I could be asked a question about the volume of concrete for the curb, and so if I could find the cross-sectional area and then accurately get the length of the curb, I can find the volume. I'm also going to try to notice if there are any geometric shapes. For example, here I have a triangle, and here I have what I affectionately call the outside area or an area of a donut. By the way, to find this particular area is not as complex as it seems. If we consider that the long radius is a big circle and figure out what the overall area of the big circle is, and if we consider the smaller radius to be what's not there, and we find the area of what's not there, we can take the gross area and subtract what's not there from it, and what we will get is the outside donut. In this case, we need to then divide it into quarters because this is a quarter of a donut shape. But where the test will really test you is, what about this radius? Because this radius interfaces with note number 3 at the top of your page. Note number 3 says, paving, curb, and gutter and radius dimensions are to pavement side of curb and gutter. That means this radius is extending all the way to the outside of this curb. We can't use that number, the 120, to get the sodded area because we'd be including a curb that is not sod. And so we would have to go to the detail about the curb, find out the curb is 1.5 feet thick or wide, and subtract that from the 120. In your practice exam, which consists of 2 parts, a morning part and an afternoon part, the morning part, question number 3, is a good example of that particular calculation. Here we're being asked to figure out how much material we need per acre to place along this sodded area number 2. And so we would need to find out the area of the triangle and the area of the donut, the quarter area of the donut, and then apply the ratio that's being given here for the amount of fertilizer. Now at the back of the test is an answer key. So what you ought to do right now is just take a moment and stop the video and do this question. And then check the answer with the answer key and see how you did. Now before you do that, I just want to point a couple things out about this shape. When we go back to this shape, you'll notice that this is an area that is this donut. And we notice that this is a triangle. However, we have to be careful about this triangle because what we want is only this part of a broader triangle. And for example, the measurement that we're given for this line over here, which is 176 feet, extends all the way to the top of the property line, and we don't want that. So we're going to have to find out this leg of the triangle from using the dimensions on the plan. When we go to do this, it might first strike us that we have 170 feet at the edge of the property line, extending from the tip of the triangle, but going all the way to the top of the property line. If we knew the distance from this part of the property line back to here, we would be able to subtract that from the 170 and get this dimension. To find that out, we're actually going to have to do something of a mental cha-cha-cha, because the only real dimension we're given that we can hang our hat on is this 42 feet that extends from the property line, but not exactly to where we want it. It extends to the inside of a column. However, we're told that from that column to the outside edge of the building is 2 foot 8. So if we were to take the 42 and subtract the 2 foot 8, we would get to the outside edge of the building. However, that is not what we want yet either, because what we want extends 7 foot 6 inches from the outside edge of the building to the point that we want. So we would now have to add 7 foot 6 inches to this point. Once we came up with the actual number from here to here, we could subtract it from the 170, and we would get the actual length of this triangle. And as you work through this, use the answer key to help you, to show you how you can get the numbers that you need. All right, turn to sheet number 2, and let's take a look at how this sheet operates and what kinds of questions we can be asked about this. First of all, notice that on the extreme left side of your plans, you have a designation of F through A. And then down at the bottom of your plans, you have a designation of 1 through 8. So for example, if I were to ask you for the intersection of A2, you would be located right here. When you read plans, it's a good idea for you to use your fingers. Actually touch the things that you're trying to find. This will make your life a lot easier. Now what we're seeing at A2, this little rectangle with the circles inside, the circles are actually piles. Remember, we're looking down at this. These piles are driven into the ground. They are then capped by forming a pile cap around the piles, putting rebar inside that pile cap and pouring it solid with concrete. This triangle mark 1 simply tells us that there is one of this type, or this is type number 1. And in the schedule, we would find out more details. Now, one of the things you're going to be tested on is simply your ability to count. And that may sound too easy, but it's not as easy as it sounds. So what I'd like you to do is pause the video right now and count how many number 1s there actually are here. Now, in the exam, you'll be given a marker, and you can just mark these off as you go along. But the issue here is accuracy, and you need to be able to count with accuracy. So try to count the number of triangle 1s here. You should have come up with 19. There are 19 triangle mark 1s. If you didn't get that right, you're going to want to work on your counting. And although, again, this sounds simplistic, after you're familiar with the kinds of problems that the exam asks, the only thing left is issues of accuracy, such as counting, and you want to practice that skill. Another issue that's here, for example, if we look between 7 and 8 and A and B, this area here, we see a concrete grade beam that is being used to support the stairs in the building. And notice there are 2 of these. So if there was a question about them, of course, one of the issues would be, did you remember to multiply by 2 if they're asking for both of them? Or are they only asking for 1 but confusing you, so you'll select 2? But we might need to find something out about this. And they show us a detail here of this as detail A2, which means that on this sheet, detail number 2 is showing us the cross-section. It's telling us that this is 1 foot 2 inches wide and 1 foot 4 inches deep. Now, we, for example, might be asked to quantify the amount of concrete that's here. So if we knew the actual length of this, another detail on this sheet is over here between 7 and 8 and A and B. We have a concrete grade beam that's being used for the stairs. You'll notice that there are 2 of these grade beams on our plans. And so, of course, any question that would deal with them would have the extra twist in it of either asking you about 2, hoping you'll just solve 1, or telling you about 2, but only asking you about 1. In any event, we have a detail about this grade beam on the same sheet that's telling us that it is 1 foot 2 inches wide and 1 foot 4 inches deep. We could be asked a variety of questions about this grade beam. For example, we might be asked about the volume of concrete in it. We might also be asked about the rebar. For example, they're telling us that there are 3 number 6s continuous on the top and 4 number 10s continuous on the bottom. It's also telling us that we have number 4 ties 12 inches on center. Whatever question we're asked about is going to involve us finding the actual length of this shape. This issue of the length of a shape that's rectangular like this goes back to a discussion that we had in the first module about how we actually determine the length of the shape. The 2 choices we have is to separate each piece and accurately record how long each piece is and then add them together, or to determine the center line perimeter around this shape, which would be adjusting the measurements. In the case of this concrete grade beam that we were looking at on the plans, the outside distance from this point to this point you'll find is 32 feet. And the outside distance from this point to this point you'll find is 12 feet. And we could either chop the pieces apart to add up the total perimeter, or we could adjust, for example, the 32-foot measure to subtract the thickness, 1 foot 2 inches, and we would get 30 feet 10 inches. So the center line measurement from here to here would be 30 feet 10 inches. Turning this way and taking the gross measurement of 12 feet, we would cut back 1 foot 2 inches, and we would get the distance from this point to this point as being 10 feet 10 inches. If we added all of them up, we would find out that the centerline perimeter, or the true length of this shape, winds up being approximately 83 and some odd feet. You're going to do this exercise because the next thing I'd like you to do is to turn the video off and do one of the problems that is on your set of sample problems, and you'll do problem number 6, which is asking about this particular concrete grade beam. Work with the numbers and determine the actual perimeter of this shape, the centerline perimeter, because you'll undoubtedly be asked questions that will require you to find the actual length of shapes like this. So turn the video off and take a shot at question number 6 in your set of questions for this plans in the morning session and see how you do. Another issue that we might see here on this sheet number 2 is you'll notice that we have some broken lines that are being drawn along here. And this is actually showing us a concrete grade beam that is used as a footer. So we have a footer designated by these dotted lines. You will also notice